Hi everybody, welcome to chapter 4 on curve sketching. So up until now, when we have gotten the the equation of a function, and you're being asked to graph it, we have to do a lot of analysis without calculus. So we find the zeros, with rational functions, we found the asymptotes, and we kind of had to fill in a lot of the blanks with testing different x values and finding the y values. But now this chapter is going to allow us to sketch curves quite efficiently using calculus, because calculus tells us where maximum and minimums are using the derivative with the idea that that's the slope of the tangent. So that can answer a lot of questions. Today specifically we're talking about how can a derivative inform us where a function is increasing or decreasing. So let's think about that. So I've started with this cubic function here. You can see the formula to the left, the equation I mean, sorry. And you can see that it is increasing until x equals -2, then decreasing between -2 and 0, and then increasing again from 0 to infinity. Remember, for increasing to decreasing, we are strictly looking left to right, reading it like a book across the page. So what does the derivative look like? Well, it looks like this blue function. So what do you notice about the derivative over the increasing and decreasing intervals? Well, notice that the derivative is positive up until -2, then is negative between -2 and 0, and then is positive after 0 again. Think about why this is true. The slope of the tangent is the derivative. So anywhere where the slope is positive, the derivative will be positive. Where the slope of the tangent is positive, that indicates an increasing function. It's on its way up. Where the slope of the tangent is negative, the derivative will be negative. Okay, so that means that the function is decreasing over that interval. And where the slope of the tangent, of course, again, is positive, the function is increasing. So that is the basic understanding that we're taking with us into this note today. So determining the intervals in which a function increases and decreases is extremely useful for understanding the behavior of the function. For functions that are both continuous and differentiable, we can determine the intervals of increasing and decreasing y values using the derivative of the function. So if you take a look at this, we say that a function is decreasing on an interval between x1 and x2 if f of x1 was higher, so greater than f at x2. Okay? And then it's increasing, if the first x value, so f at that x value, is less than the second y value. Okay, so for continuous and differentiable function f, on a decreasing interval, the derivative of the function will be negative. And on an increasing interval, the derivative of the function will be positive. Okay, so take a moment to get out a ruler and maybe draw some slopes of tangents here. So notice that on a decreasing interval, the derivative is negative because the slope of that tangent line is positive. And on an increasing interval, the slope of the tangent is positive. Okay, so the derivative is positive. All right. So now we can use that information to solve problems. So this is actually the function that I showed you on the graph. So let's actually go through and use the calculus to show the increasing and decreasing intervals. So the first thing we do is find the derivative. So dy dx is equal to 3x squared plus 6x minus 0. So then we set the derivative equal to 0 and solve for x to determine the turning points of the function. So remember, setting the derivative equal to 0 will give you where there is a horizontal tangent, and where there's a horizontal tangent, that indicates a turning point. Could also be just a horizontal tangent, but for now, we will use it to test if it's a turning point, I should say. So you'll see what I mean in a minute, or maybe in a future note. So 3x, x plus 2. So x equals 0 and x equals -2 are possible turning points. Okay, so now we just test the intervals from step 2 to determine where the derivative is positive or negative. So we look before -2, between -2 and 0, and after 0. Okay, and remember, we're looking at the derivative, not the function. So the derivative here, if you put it into 3x, a -2, you would get a negative. And then a -2 plus 2 would still give you a negative, so that gives you a positive. So it's increasing up until -2. Then between -2 and 0, that first factor would be negative, but then that number plus 2 would bump you up into the positives, so that gives a negative result. And here both results would be positive, again giving a positive result. So now we interpret our solutions. So a positive derivative means that it's increasing here. A negative derivative means decreasing. And a positive derivative, again, means increasing. Okay, so then we can, again, show that on a graph. So that was right. So it's increasing to decreasing to increasing. You can also use logic and reasoning to think about the fact that this is a cubic with a positive leading coefficient, so this behavior should be consistent with your understanding from functions, but you should still use calculus for the analysis at this time. Okay, now we get to a function that we're not as sure how it would look, so we go through the same algorithm to determine where it's increasing or decreasing. So we're going to find the derivative, so dy dx. This is a rational function, so we use the quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Okay, so when we collect like terms and expand, you get negative x squared, I think plus 1, yeah, plus 1, over x squared plus 1 all squared. Okay, so now we want to set dy dx equal to 0. So remember, when we do this, we just can set the numerator equal to 0 since the denominator will cross multiply away. So we get x squared equals 1. So x equals, careful, plus or minus 1. Okay, so now step 3 is to test our intervals. So before -1, between -1 and 1, and after positive 1. So remember, we're looking at the derivative, not at the original function. So we're looking at f prime. So when we put -1 into here, we get negative, or something that's negative, sorry. You get a positive number that's quite large, because if it's less than -1, it gets bigger. And then we make it negative plus 1 is still going to be a negative number on the numerator. Sorry, you know what? I'm going to do this in a different color, just so it stands out a bit better. So you get a negative number in the numerator here, and then you're always going to get a positive number in the denominator based on the fact that the quantity is always squared. Okay, between -1 and 1, so think about like 0. If you put that into here, you get a positive numerator over a positive denominator. And here you get a negative numerator again. So this ends up being negative, so it's decreasing between anywhere less than -1, increasing between -1 and 1, and then decreasing again after 1. Okay. So this is useful information to draw a possible f at x when you're given f prime at x. Okay, so here in this case, we are given f prime at x. So how can we draw a possible f at x given the derivative? Well, notice that when the function is positive, here the function will be increasing. Also, anytime where there is an intercept, we can interpret that as a turning point, okay? Because remember, when f prime at x equals 0, that can be interpreted as a turning point. So a local max or min. supposed to say point, not turning point. Okay, so this is going from positive to negative. So that means that so I'll put a possible up here. Okay, so whatever the slope is at this spot, that's what this value would be. So it looks to be about 1. So the function would be increasing. And then after that point, it's going to be decreasing again. So what does this minimum of the derivative mean? Well, the minimum of the derivative means the steepest point of the curve. So we can kind of put something there. And then this will have a turning point, maybe potentially something like that. Okay, it'll be a minimum because it's going from a negative, so decreasing, to an increasing. So then we can go down and then go back up again. So our curve could potentially look something like that, where again, this minimum represents the steepest point, and this here represents a turning point, and then where we go to increasing again. All right, so let's make a summary here. So if a function is increasing on an interval, that means the derivative is positive. If the derivative is negative, that means we're decreasing on that interval. If you have a local maximum, that's a change of increasing to decreasing. That means you have a 0 in your derivative. So the change is from positive to negative. And if you have a 0 where it's changing from a negative to a positive, that results in a local min. So that would be decreasing to increasing. So there you go. That's how you use derivatives to determine information about where a function is increasing or decreasing. Thanks for watching. Hope you learned lots.